Let's get started. In the last lecture, we studied the current flow in a PN junction. So, today, let us start by asking a very simple question. Is a PN junction, we also call it a diode, PN junction diode, a linear device or non-linear device? To understand that, we'll have to analyze the current voltage characteristic. For a linear device like a resistor, the voltage is proportional to the current, right? P equal to IR. What happens in a semiconductor diode, PN junction diode? Well, it is non-linear because we saw that the current is going to exponentially depend on the voltage, right? So it's a non-linear device. Okay. If it is a non-linear device, can we describe it in the form of resistances and capacitances? Okay. Can we model it as a combination of resistances and capacitances? Because if you remember, in the forward bias, after the threshold, the current seems to change linearly, right? If you go to very large voltage ranges, of course, it is going to be an exponential, truly exponential. But then you could approximate it by a fixed resistance, right? So current in the vertical axis, voltage in the horizontal axis, you see that above the threshold, it's sort of a straight line. You can try to model it. So is there any capacitance associated with the diode? That is what we would like to answer. Why are we interested in capacitance? Well, it turns out that the product of resistance and capacitance is one of the most critical parameters in the operation of electronic circuits. We have already studied, you must have studied in the basic circuits course, the product of R and C, RC represents the delay, right? RC delays we call them. So if the product of R and C is large, the electronics cannot work at a very fast speed. So because essentially when you look at an electronic chip, be it your mobile phone or a computer or a laptop, essentially what you have is gates, digital gates, which are working with zeros and ones. And there is a continuous switching between 0 and 1, right? And we are trying to compute. So all the numbers are being represented in binary, in the form of zeros and ones. And then you do computations on that, and that's why you have a computer, right? So the speed with which you can make these calculations is going to determine fundamentally on the product of R and C. Okay? So we would like to understand whether the diode has a capacitance associated with it. Okay? And it turns out that there is definite capacitance in a diode. And at least in one of the forms, it is relatively simple for us to analyze. Okay? So think about this. So you have a PN junction with an applied voltage. And for now, we will consider the reverse bias. Okay? We will not look at the forward bias, only the reverse bias. So what happens in the reverse bias? Okay? So let's consider that we apply, what is after all a capacitance? Capacitance is simply dq by dv. Right? I take a piece of, let's say a parallel plate capacitor I apply a certain voltage, I make a small change in the voltage, I'll see that the amount of charge on the plates is going to change by delta Q. So the derivative dq by dv is essentially your capacitance. So if you have a parallel plate capacitor, this is linear, so it will be C equal to Q by V. Okay, so that's why Q equal to CV, right? We write it all the time. So that works for a simple parallel plate capacitor. But for a diode, we need to analyze what happens to the charge as you change the voltage. Okay? That will give us the capacitance. So how do we do that? Let's go back to the basics and let's look at the space charge in a diode. Okay, what we'll do is we'll just say, let's say we'll apply a voltage VA, we'll consider that, and then we will change that voltage to VA plus delta V. So I'm adding a small voltage into that. What happens to the charge? Okay. So without all this, if you look at a PN junction, you will have, as a function of x, you have something, and then you can plot rho. We have done it multiple times already. So what will we see in this situation? We'll see that there is a space charge in the n-type region, which is going to be positive, and there is a different width, okay, negative space charge in the p-type semiconductor, and we call this as xn and this as minus xp. The junction is essentially x equal to 0. Right? This is 0. So now what we want to understand is, this is, let's say, at a certain voltage. Okay. So let's say this is the width. Let me put this here. I'll trace the small thing here, and I'll say that this is my width. Okay. W depletion with applied voltage VA. Okay. I do that. Applied voltage VA. Now I'll change my voltage. I'll make it V plus VA plus delta V. What do you expect? Let's say it's increasing. Okay, we understand that we are applying in the reverse bias, so we are having a larger reverse bias. So what do we expect? We know that the depletion width increases. Why should it increase? Well, essentially the external terminals are going to draw the carriers out, because of which the space charge has to increase, right? So what will happen? Let's say this will increase to this point. To this point, right? So this is additional delta Q that is introduced due to delta V. And this is also same. This is going to be minus delta Q that is introduced. Okay. So what happened as a result of application of a additional voltage dV? The depletion region has become wider. So this is my new width, W depletion, with VA plus delta V, right? So once I know this, I can compute what happens to the capacitance, right? What is the width of a depletion region? We have derived this expression a couple of lectures back. W is going to be 2 epsilon silicon by Q Na plus Nd divided by Na Nd times, it was built-in voltage, we left it as built-in voltage, but if you want to do it at any arbitrary reverse bias voltage, you could simply write it as, any arbitrary voltage, you can write it as VBI minus VA. Okay. The whole thing is under square root. Okay. As you go to stronger and stronger reverse bias, VA will be minus VR. If you take VR as the reverse bias voltage, the VA will be minus VR, so that will increase, width will increase. Okay. So in RB, this will be VBI plus VR. Okay. So as you increase the reverse bias voltage, it will simply increase the depletion width. Okay. So far, no surprises really, right? So what is this change in charge, dq? Okay. If we do that, we know the capacitance. Okay. So to compute that, what we have to do is remember what is the charge. Okay. And before we do that, please think about why I increased it like this. Okay. Why not I keep the width constant and increase my space charge? So there is a reason why specifically I'm drawing it like this, right? Extension. I'm extending the depletion region, but not increasing it on the vertical axis. Why is that? Right. Think about it. I mean, it's very clear. It should be very clear by now that it's uniform doping. So you can't change the y-axis. This is going to be determined by your Nd, and this is going to be determined by Na. That cannot change. That's the lattice fixed charge. We can only change the extent to which you remove the electrons or holes. So on the x direction, you can change. Okay. All right. Let's come back to the charge. What is a charge? The charge was simply Q times, let's take Na on the P side, XP, right? This was the total amount of charge because density was Na times the width will give you the per unit area and then into Q, the charge. And we have already derived an expression for this. We said this was QNA and XP was proportional to ND, right? So there was this ND divided by NA plus ND times width. You see, now we have managed to bring in the width, and width has a voltage dependence, right? So now all I have to do is simply compute capacitance C equal to dq by dV. So take a derivative of q with respect to V, okay? And I will let you do that, okay? I mean, it's simple algebra. It's simply square root of, voltage you have to take. So you have to do it carefully, but it can be done. We are not going to gain anything much, by just doing it on the paper here. So I'll give you the final answer. Okay. If you do this, well, I mean, yeah, if you do all that, the answer is going to be epsilon silicon divided by W, depletion. The total capacitance of a PN junction is simply the relative dielectric, the permittivity, dielectric permittivity divided by the depletion width. Okay. It should actually surprise you. Oh, well, I mean, it looks very, very deceptively simple, right? Remember, if you have a parallel plate capacitor, parallel plate capacitor with, plus Q and minus Q, what was the capacitance? It is simply C equal to epsilon A by D, right? The distance, D. If this distance between the plates was D, this is epsilon A by D. Well, if you talk of capacitance per unit area, okay, C per unit area is epsilon by D. So simply the dielectric permittivity divided by the distance between the plates. There is no reason for us to expect that the capacitance, the depletion capacitance should be epsilon divided by the width of the depletion region. Or if you have a way, I mean, you must be remarkably smart. At least I didn't think about that way. Okay? But it turns out that this is entirely different charge configuration, right? In the parallel plate case, you have two unique charge plates, plus Q and minus Q. Right? But in a PN junction, you have a distributed charge. The charge is not at one location xn or xp. It is distributed over a region from 0 to xn and then from minus xp to 0, right? So even though you have this distributed charge configuration, the way the math works out is, it come back to this. I mean, there is an indirect way of thinking about it, but anyway, I'll leave it. So the answer is intriguing, okay? It's all the more interesting because if you have a parallel plate capacitor, it does not exhibit any voltage dependence. It is simply dependent on the material parameters and the distance between the plates. Whereas if you have a PN junction's capacitance, C depletion, this is going to be proportional to 1 over width has a square root of voltage term, VBI plus VR. So this is a voltage dependent capacitance. Voltage dependent capacitor. Okay. And if you do the math carefully and rightly, you should also find out what are the units, and the units turn out to be farad per centimeter square. That's how we'll represent the capacitances. Okay. All right. So what is it useful for? Okay. It has applications. Okay. One of them is that, okay, yeah, if you do all that, I just wrote out the expressions, you'll work it out and you verify that this expression is indeed correct. One of the important points is, I'm sorry, well, yeah. So, if I look at capacitance, right, as I said just a moment back, it is 1 over root of voltage. If I write VA equal to minus VR, okay, I'm applying reverse bias. That's all I want to explicitly make it clear. Okay, so then I can compute what is 1 over C square, C depletion square. Okay, versus, if I do this, it will have this entire, W square on the top divided by epsilon silicon. Okay, and if you do the full analysis, it's going to be some voltage, VPI plus VR, that will be there. But then there's going to be some coefficient here, and that coefficient turns out to be this. Okay, well, yeah, we are also making an assumption here that, let's assume a one-sided junction. That means, let's say, assume Na is much, much greater than Nd, one-sided junction. If you do this, then the slope turns out to be simply 2 by epsilon silicon Q times Nd. The reason this is useful is we can measure it experimentally. We can apply a reverse bias voltage and keep measuring capacitance at different points. We have what is called as an LCR meter that is used to measure the capacitance. And so if you measure that and plot voltage versus 1 over C square, you get a slope. And from the slope, you can find out what is the carrier density in your semiconductor. Because carrier density is essentially, doping density, not carrier, doping density. Because doping density is something dictated by the, in the doping process, right? It's done by the manufacturer, but you can fabricate a device and actually verify what is the doping concentration. Okay. So this is one of the uses. And of course, if you extrapolate it to the x-axis, you get the built-in voltage. Okay. So this is a very powerful technique to actually find out the material, the doping concentration and the built-in potential for a p-n junction. That's why it's used. And once you know this, you can easily, calculate. So let's say, why do I want to know this? I mentioned that, RC, right? RC is going to influence. So if my capacitance now, if you calculate it, it will turn out to be a few picofarads per centimeter square or something like that. And then let's say if I fabricate a device, if I want to fabricate a device which is having a diode which is having 5 centimeter square area, a large diode. If I do that, the capacitance is going to be large, and because of it, it's going to be slow. And this is one of the reasons why semiconductor devices are always, over last 50 years, they have been continuously shrunk in size. So much so that today we have only a few, the MOSFETs, which are 5 nanometers technology or 7 nanometer technology. So they're very, very small devices. The reason for that is once you make it smaller, the capacitance reduces, RC reduces, so that circuits are faster. Okay, that's one of the primary driving forces. So let's take a few numbers and see what it is. Okay. Well, this is again a problem from the textbook, 7.5. You can go back and verify the solution as well. And you're asked to calculate the junction capacitance for a PN junction, assuming, okay, all the parameters are not given, but they're all from another example. Okay. So if you're asked to calculate the junction capacitance, first thing you would do is simply the width of the depletion region. And that is going to be 2 epsilon silicon. You need to remember this. And if you do it the way I do, you'll remember it in a few times because I'm just speaking about it every day, right? Minus VA. This is half, right? This is your depletion width. How much is it going to be? We have seen that this was of the order of, 0.5 micron or something. Order of a micron, less than a micron, around a micron. Okay. Remember, you should compute this and verify, okay? We have done it once in the past, that's why I don't want to do it. Okay, and I don't remember what are these doping concentrations for this example. For us, we need the approximate numbers, you will do the exact calculations. So once I do this, C depletion is going to be epsilon silicon divided by this number. So you need to be very, very careful when you're solving semiconductor problems. For one aspect, epsilon silicon is 11.7 into the permittivity was 8.85 into 10 power minus 14 farad per centimeter. Remember, always we give it the units in centimeters in semiconductors. Okay, that's the safest thing to use. So width in centimeters. Well, this is going to be 0.5 into 10 power minus 4 centimeters. Okay, so you see that what is this going to be? something in the order of 11. I'll make it 10. That's one also I'll make it 10. 10 into 10, 100. 100 into 10 power minus 10. Okay, farad per centimeter square. So this is equal to 1 picofarad per centimeter square. Of course, this is not the correct solution for the problem, by the way, right? You understand that, by now. So when I show these numbers, these are all rough numbers. I don't want to sit with the calculator and make sure that I do the exact numbers. They are there in the textbook. You please open it and verify your answers. Before you verify the answer, I would suggest that you solve it by yourself and then use the textbook as a reference to compare. That will help you iron out any small mistakes that you make. Okay. So that's it. Well, yeah, we only talked about the depletion capacitance. You might ask, what about the forward bias? Is there any capacitance? It turns out that even in the forward bias, there is a capacitance which we call as diffusion capacitance. Okay, this is in the forward bias. The functional behavior is different. It's essentially something to do with how much time the minority carriers are going to spend in the semiconductor. Okay, so it is related to the minority carrier recombination time, and it's a little bit involved for us right now. It turns out that the depletion capacitance is much more widely applicable. There is a reason for that. When we come to MOSFETs, we'll talk about it. So we will not really be talking about diffusion capacitance in this course, other than to say that it exists. But in a lot of cases, you will have the PN junctions in depletion mode in a MOSFET. That's why we'll focus on that. Okay, that is going to be much more significant for us. Okay, so yeah, I hope that you understand the importance of capacitances, and then you're able to compute the capacitances for a simple PN junction. So when we talk about MOS capacitors, we will really use these capacitances, left and right. I mean, we can't describe without that. Okay, so please make sure that you follow it. If not, go back and review this lecture, and I'll see you in the next video. Thank you.